Okay, in this last lesson video on magnetic induction, we're going to talk about eddy currents, which is perhaps the most fun and most useful application of induction at this point. And so the only thing that I hope you take away from this video is that by the end of this lesson, you can explain how Lenz's law results in magnetic braking through the generation of eddy currents, typically in large metal conductors. So to get to that point, I thought I'd do this step by step and taking first a big step back. So we've said before that permanent magnets and electromagnets are essentially the same sort of phenomenon. In the permanent magnets, we have north and south poles. And in solenoids, for instance, when we generate electromagnets, we also have north and south poles. And so when we say that a field points in a certain direction, like the field points up here, what we're essentially saying is the field points from the north pole to the south pole. So essentially, if something points out, a magnetic field points out of something, that corresponds to a magnetic north pole. That kind of is important because that tells you when there are attractive or repelling forces, right? So if you have two like poles, they will repel. Only attractive opposite poles will essentially attract. That plays a role then in the whole phenomenon of induced currents and induced magnetic fields. And so if you consider this loop example that we've seen before, so if we change magnetic flux through that surface enclosed by this loop, in this case, Faraday's law will tell us that there's an induced EMF, an induced current, and an induced field, at least if we have a closed loop where a current can flow. So in this case, if the magnetic flux increases, that means that the magnetic field gets stronger in the upward direction. Lenz's law will tell us what the direction is of that current. It tells us that we're going to generate a current to essentially generate a downward magnetic field to counteract this change in flux. Okay, and so to get a downward pointing magnetic field, what we need to do is to have a clockwise current. So with a clockwise current, indeed, we make a downward magnetic field that opposes that change in flux. So what does that mean? Essentially, it means that the magnetic field we generate in this loop is one with the north pole facing down, because that's the direction that the field is pointing to. Okay, so the first quote here is how we've seen Lenz's law. We've said that the current or EMF that is induced by a changing magnetic flux is in a direction such as to oppose a change in flux. Now, we've seen in the previous video, we've talked about motional EMF. So we've seen that you can also induce currents and EMFs when you simply move a conductor in a magnetic field. Well, it turns out Lenz's law actually expands to that case as well. It says that the current or EMF that is induced by a conductor moving in a magnetic field is in a direction such as to oppose the conductor's motion. So if you move a conductor in a magnetic field, the current that's induced is such that it's trying to stop you from moving it, or making it much harder for you to actually move that conductor. So you really can feel that force. So let's actually get through that. And I thought to start with an example that in principle you should be able to work through on your own now by using Faraday's law and Lenz's law to figure out what's happening. So here are two different scenarios. They're very similar, but they're slightly different. In both cases, we have a permanent bar magnet that's falling down through a conducting rung. In case A, it's a solid ring all around. In case B, there's a small gap here that's cut open, and essentially, so there's a break in the conducting material. And so here's the question: what will happen to the magnet in each of these cases? And so this is a good time to actually pause and think about this for yourself. Try to do this step by step in each phase of the motion. What is really going to happen? Can you work out step by step what the outcome will be? So in the first phase, let's look at this fully closed ring. And so we drop the magnet and it starts approaching the ring. So what's going to happen? Well, as we bring the north pole closer to this ring, we'll actually get more and more field lines through this ring, meaning that the field strength increases. So that also means that the magnetic flux increases. An increase in the magnetic flux means that we'll get an induced current. And Lenz's law tells us that that induced current is going to be such that it's going to try to counteract that change. Okay, so the induced current must be counterclockwise. And if you have a counterclockwise induced current, then the right-hand rule tells you that the induced B field is actually pointing up, right? Is that opposing that increase in flux? Well, yes, it is, because it's this situation where you have an upward pointing magnetic field is the same as having the north pole of a permanent magnet sticking out. Okay, and so now what you do is you exert a repulsive force on this magnet. And so that means that there's now a net force on that falling magnet, which is not just the force of gravity, it's the force of gravity minus the force induced by that induced magnetic field. And so what you find is that the downward acceleration is actually smaller than it would be in free fall. And so it slows down the fall, although that's not really technically accurate. It's not that the velocity is actually decreasing. It's just that the acceleration is not quite as fast as it would be in free fall. So it's a slower acceleration than in free fall. So it's slowing down the gravitational acceleration. Okay, but often it's called that it's slowing down the fall. Okay, now when our magnet is completely within the ring, so bar magnet and a solenoid is the same. In principle, a perfect solenoid has a zero field outside and a constant field inside the solenoid. So essentially that means that in this case, as long as the magnet is entirely within the ring, the flux is constant. Therefore, there's no induced current, no induced B field. And so the net force is actually the force due to gravity. And so you'll go back to free fall while the entire magnet is within that ring. But now as the magnet comes out at the end and it's leaving the ring, the situation is different again. So now the flux is actually decreasing through that ring. And so again, we're going to have an induced current that's going to result in an induced magnetic field. That's going to oppose that decrease. So now we have the north pointing down of our bar magnets, what we're going to create. And so the flux is decreasing. We want to have a nice strong field. So the induced field will actually try to strengthen in the same direction because we're losing magnetic flux. And so now we have an induced current which is clockwise. That will generate an induced field that's actually pointing down, right? So with the north equivalent to the North Pole facing down to kind of counteract that decrease in the magnetic flux in this case. So now what you have is the induced field actually exerts an attractive force on that magnet. So now it's actually pulling that magnet in an upwards direction. So again, our net force of gravity is our net force is not just the force of gravity, it's the force of gravity minus the force due to that induced magnetic field. And so again, the downward acceleration is smaller than in free fall. And so that induced field once more slows down the fall in the same sense as we talked about before. And so as you have your bar magnet falling through the conducting ring, there are certainly two phases where you actually see that the induced field works against that motion that is causing the changes in the magnetic flux through the loop. What if our ring is not closed? What if it's open on one side? Well, so our magnet is going to approach the ring. We're still going to have the case that our flux is going to increase. So that's going to induce an EMF, but there's no current that can flow. So therefore, there's not going to be an induced magnetic field either. And so consequently, there's no opposing force. And we find that the net force is just the force of gravity. And so we get free fall acceleration all the way through this ring here. Okay, now on the other hand, suppose that you have not just one closed ring, but you actually stack a whole set of these closed rings. As the magnet is going through, it's always either approaching or leaving one of these rings in the tube. And so what you get essentially is the equivalent of a conducting tube. And so here's a demo. It's a very commonly done demo where essentially you have a copper tube. And so copper is not a magnetic material. It's just a conductor. And if you drop a magnet through, that induced field will actually slow down the fall of that magnet quite significantly compared to just a regular other metal material. So have a look at that. That shows you that those forces can be quite significant, that effect of slowing down or trying to oppose the change in motion can actually be quite significant. So with that example, I think it's now perhaps easier to understand how eddy currents actually form. So now consider a large metal plate like this plate illustrated here. Again, we're going to look at this in two ways. We're going to look at this from the point of view of forces on moving charges, and then we'll look at it from the point of view of Faraday's law and Lenz's law. So we have this big plate here, it's large, and we have a fairly small area here where there's a magnetic field, and so the magnetic field is pointing down, right? The north arm's right here, the south pole would be below the plate. So with downward pointing magnetic field, now suppose that electrons are the charge carriers, and suppose that we pull this plate in the right-hand direction. So V cross B would actually point upwards here, but since the electrons are negative, the force on the electrons actually is going to be in that direction. Okay, so the electrons are going to move in this direction. It's a bit confusing with electrons, I apologize for that. Electrons moving down in this direction means that the current is actually moving upwards, so the current is moving up in that direction. So pulling the plate results in a force on the charge carriers. So the charge carriers move perpendicular to your direction of pulling that plate out. That generates a current perpendicular to your motion. Now we have to consider that there is a force on this current, right? It's a current that goes in a metal plate, not just on a wire, but it's still a current. And so the force on that current is IL cross B. The current is going up, field is going down. So the right-hand rule tells us that this will result in this backward force F2, right? So there is an opposing force to your pulling the plate under that magnet, right? And so that's how you can see, like, yes, there must be a force that's opposing that motion, and this is simply from the point of view of the forces and the resulting motion of the charges in that conductive material. You can also look at it from the point of view, of course, of Faraday's law and Lenz's law. And so suppose that we mark an area on our plate, like with that yellow circle right here. And so we're going to say that this is a representation of, you know, what could be the equivalent of a ring. It's a solid metal plate. So just like when we talked about the bar magnet falling through the ring, we can actually distinguish the different phases in this process as we actually pull the plate through. So as we approach the magnet here, the flux through this ring is going to increase. Again, our north pole of our magnet is on the top. So there's a downwards increasing flux. So from Faraday's law and Lenz's law, we'll see that that will generate currents and induce a field that will be pointed upwards. So we must generate a current such that the magnetic field that results is pointing upwards. And so that will be a counterclockwise current indicated here in red, and that will result in the induced field, which is pointing upwards. So the induced field is marked in blue right here. Okay, now as the ring moves under the magnet completely, essentially there's no change in magnetic flux at this point, and so there's no induced magnetic field at that point. But as we now leave the magnet again, now the flux is decreasing, so the downward flux is decreasing. Lenz's law will tell us we'll try to counteract that, so we're going to add some magnetic field to counteract that decrease. So the induced magnetic field must point down. Therefore, the induced current, as indicated here, must be clockwise. Okay. And if you have that clockwise current, then you will generate that downward induced field. Now, let's go back here. So we saw in this case, we have our counterclockwise current and an upward pointing magnetic field. So now we have essentially the situation that we have a north pole facing a north pole, which is slightly ahead of the magnet. And so you're going to have a repulsive force on this side, right? So this magnet is going to pull back this induced field against your direction of motion. Similarly, when you're on the other side, when you're trying to pull this away, so now we have our north pole of the induced field pointing south, pointing down. So now this is the induced field is the equivalent of showing the south pole on the top. And so the north pole of our permanent magnet will now be an attractive force to the south pole of that induced magnetic field. And so now you'll get an attractive force. And so in both cases, what you get is that there's a force that's induced on your metal plate that essentially stops you or makes it harder for you to actually pull that plate out. And so in the metal, these are the currents that exist, right? So you get a current in this direction, as we talked about before, because the charges, the magnetic force on the charges. Outside the region of the magnet, these currents can easily reconnect. The exact size of these loops here depends on the resistivity of your material, depends on the magnetic field strength, and that sort of things. But in any event, these are eddy currents. So they're closed loops. They're called eddy currents because they look a little bit like eddies that you can find in the water or in your bathtub. But so they are these roundish type currents that you get in large metal areas. And so you have currents here going counterclockwise and clockwise here, but underneath the magnet they go in the same direction here. And so the induced currents also can flow in these solid conductors, and so those are the ones that are called eddy currents because of their similarity to eddies in rivers. And typically in metals that are good conductors, the resistance is low, so these currents can actually be quite large, and so they result in a lot of energy dissipation. So what you'll see is that if you have induced currents in these metal plates, you will actually heat them up. So by pulling the plate under a strong magnet, you can actually heat up that metal quite a bit. They also cause magnetic friction. So if you pull on that plate, you actually feel that induced magnetic field is counteracting your motion, and that results in what's called magnetic braking. And so there's many applications of this of these eddy currents and magnetic braking in electric cars, roller coasters, power tools, all that sort of things. And there's one other application. So let's look at a few applications of eddy currents right now. So one thing that you may have been subjected to is actually going through a metal detector, and typically that's where eddy currents play a role as well. The way a metal detector works is you have a transmitter coil and a receiver coil. Your transmitter coil essentially has a current that generates a magnetic field that induces a current in your receiver coil, and you actually measure that current. And if you have a strong current, essentially you know that there is nothing in between your coils. But if there's metal in between, okay, now you'll have eddy currents that operate in that metal. And so those actually dissipate quite some of the energy. And so you'll still get some induced current in your receiver coil, but it's a much weaker current. And so that will then trigger the alarm. One of the key applications is magnetic braking. And so here's one example of how you can actually think about magnetic brakes. I have a few more examples coming up. So suppose that you have a metal disc that's essentially rotating like this, and there's only one small area indicated here where there is a magnetic field acting on that metal disc. What is actually going to happen? Well, so if you consider this cross-sectional area B here, so the field is pointing into the page, okay? So the velocity of your disc is to the left here, okay? So that's going to result in a current V cross B is essentially pointing down. So you'll get downward currents. It's indicated by these arrows. Get downward currents in this region where you have the magnetic field. If you have a downward current in that magnetic field, you use your right-hand rule. What you essentially find is that this results in a force IL cross B, and that force is essentially against the direction of motion. So that's just the same as before. If you rotate this metal disc in the presence of that magnetic field, the induced field will result in a force that works against your original motion, and so that will slow down the rotation. And so magnetic brakes are very useful. You don't need to be in contact with your brakes, so you can actually use magnetic braking without causing any wear and tear on your brakes. And so it's often used in hybrid cars and in electric cars. A big advantage, if a regular car, you have to stop, you have to apply the brakes, and essentially it's friction on the pads on the disc that slow the car down. So it's kinetic energy that gets transformed into heat, and your brakes actually wear. In an electric car or a hybrid, what you do is you just release the accelerator. Now you'll get some magnetic braking going on. And we've talked about electric motors. You can actually invert an electric motor and turn it into a generator. And so you can use actually quite a bit of the energy of your kinetic energy and turn it back into battery power. So you can actually regenerate energy in your battery while you're using this electromagnetic braking. Another example of magnetic braking is a metal pendulum in a magnetic field. So suppose that you have a pendulum like this, you have a solid metal disc that goes into this magnetic field, again, pointing into the page. Velocity is going in that direction. What will actually happen? Well, so you'll exert a force on your charges. V cross B essentially tells you that there will be a current flowing in the perpendicular direction upward here. In this direction will be the current. There will be a force on that current. So now it's I cross B. If you calculate that, you actually find that that force is backwards. Okay, so your induced current points in this direction. So that can make these eddy currents right here. Now the currents here actually don't really play a role. They're not inside your magnetic field. It's the currents here that move in this direction. They move in that direction because of the magnetic field. But because they are in the magnetic field, they also experience this backward force here in that direction, right? That's IL cross B, where B, of course, is the applied field and not the induced field. So the force goes against the direction, and this will slow down your pendulum, okay? Later, if your pendulum is leaving the magnetic field, it's a similar situation. You're now decreasing the flux here, so you'll get an induced current that's now going clockwise, okay? And so because you have a clockwise current, here again, doesn't really matter, there's no magnetic field. On this side, in the magnetic field, you'll experience a force which is now going to the left, and so again, you experience a backward force. So again, your metal pendulum is being slowed down. And so here's a demo from in our physics lab where we have such a disk. It's not touching these magnet poles here. It can just swing freely. It's just if you put this metal plate in there, you generate eddy currents and magnetic braking that actually stop down that pendulum very, very quickly. Now we have another half on our metal disc in the pendulum, which is slotted, and if you actually put that between the magnets, what you see is that the effect of magnetic braking is enormously reduced. And these slots make the spaces that you have to generate eddy currents much smaller, and so you can only have small eddy currents in these smaller conducting areas. And so that greatly reduces the efficiency of magnetic braking. And so if you repeat this experiment, but now with this side between your magnet poles, you'll see that they're still braking, but it's far, far less than what you would get with a full disk. And so magnetic braking is great because it's a very efficient way of braking, and there's essentially no wear and tear on either your magnet or your conductor, because essentially they don't really touch. And for that reason, it's also used in cases where you need to be able to accelerate or decelerate quickly and safely and not produce a lot of wear and tear. And one such example is roller coasters. So these things here on both sides, actually, these rails are north and south poles of magnets. And as a conductor comes through, essentially it will use magnetic braking to very quickly stop your roller coaster. And so finally, I'll post a few more videos on OWL actually, where you can see what happens if you're near strong magnets What happens if you can generate eddy currents? There's all sorts of weird things that happen. Things fall extremely slowly, or they don't seem to fall at all. They can levitate, they can float. But also the forces, the magnetic forces on some of these metals can be quite strong. So I leave that in a separate set of videos, just for your enjoyment.